everyone, back to Lucas's whiteboard. So we were talking about Chapter 8 hypothesis testing. Remember, there were 4 steps. State your hypothesis, and there were 2. The null, which means there's no change, no influence, and the alternative H1 or HA. And then we have our second, set the criteria. We're talking about the alpha level. We were talking about a critical region and degrees of freedom. In the particular example I'm going to give you, there is no degrees of freedom because it will be the one sample z-test. But the further ones we'll talk about later on throughout the videos will include degrees of freedom. So there's 3 pieces to that. The third is compute and analyze. In other words, you're going to run the test, and the results you'll compare back to steps 1 and 2. And so the final thing you would do is make your decision, and you'll report that in APA format because we're talking about psychological statistics. So now let's break this down and kind of understand a little bit. So we're back to Lucas's room and his little whiteboard, and let's talk about now what this would look like. So first of all, let's think back to the idea of the normal bell curve, right? Or in this example, the normal distribution. In other words, if you're going to run a one sample z test, right? Z like zebra. A one sample z test, you have to keep in mind that you have a couple of requirements. One of the first is that the actual distribution, meaning that if you ask every single person that fits the criteria of your population, and you were to ask them all that particular question, it would actually form this normal bell curve. We would be completely symmetrical, 50% on the left, 50% on the right. What is the right and left? Basically, the number here in the middle is represented by the mean. So we're talking about 50% above the average, 50% below the average in terms of their opinion. We're also talking about the second component of this normality is these, right, as I call the notches on the belt. In other words, the spaces between each of these is called the standard deviation. The standard deviation is the average distance that every single person is from the average. And again, the average was that one voice or that one number value that represented the entire group. And so how far or close everybody is from that, you would take everyone's distance above or below this average, add them up and divide by how many you had, which is the process of the average, and then you would get a new average. But because you're taking people's distances from the average, that new average you calculated would be called the standard deviation, represented by, in the population, the sigma symbol, the Greek letter. So standard deviation in a one sample z-test, as we learned in class, is basically 1. So the mean is 0, standard deviation is 1, so 1 above is 1, 2, 3, and if we're going below, -1, -2, and -3. And so looking at this curve or this distribution, we have to now start thinking about it. What are the different pieces and how does this tie back into hypothesis testing? Well, first we're going to have a null and alternative hypothesis. So let's describe whose house is where. So if we're talking about the normal distribution, 68% of people, or about 68%, fall within one standard deviation above and below the average. So we're talking about 34% on the left and 34% on the right in terms of what the average or collective voice was. And so if we start looking at that, the alternative of the null hypothesis says, well, where's the 95%? We always think about 95% of people think and believe something. And there's always that 5% that's outside of that, either the 5%, the 2%, anyone outside of what we consider the norm. So then if we go on beyond that, we actually go to 2. But we're not really at 2 like I showed you guys in class. We're actually at 1.96. Negative 1.96. And positive 1.96 would actually give us exactly 95%, right, in this whole space. 95% of the population. So anything outside of that would then be 5%. And if we can see this, we can see we have 2 tails. We have 2 spaces here, a small tail here, and a small tail there. And if 95% lies in the middle, logically, how much lies on each of the sides? We'd have to split it in half because there's 2 sides. So we'd actually have 2.5% here and 2.5% here in these tails. Inside the body, we had the 95%. So if we're looking at this then, whose house is what? HO means that there is no change, no difference, no relationship, or no influence between what is being tested. So let's put this in real context. Let's think about anxiety. And if we're talking about a treatment or program to help people or teenagers with anxiety. And there's many programs out there helping teenagers with anxiety. The majority of the programs cure people. Do they really cure? Not really. They help and support teenagers to lower their levels of anxiety. And it doesn't help every single person that goes through the program. We always hear that idea of it depends. So in reality, it helps the majority, 80%, 90%, 60% of people that run through the program actually come out successful and lower their levels of anxiety. So we're talking about, in this example of statistics, 95% of programs are successful in helping a majority of teenagers who suffer from anxiety. And some would not necessarily help them. So then what do we want to be? We want to either be different or we want to be like everybody else. If we want to create something like as everybody else, we're talking about the 95%, the norm. So if you want to be within the 95%, the norm, you want to have no difference between you and them, then didn't I just tell you that the null hypothesis is there's no change, no difference, no relationship between what you're doing and everybody else is doing? So you create an anxiety program that's going to give the same result as everybody else's anxiety program. You would be in the 95%, so you would be in the HO's house, the null hypothesis. But what if you wanted to create an anxiety program that was distinctly different than all of the other anxiety programs, and it cures or supports and helps maybe 90, 80, or 100% of the teenagers that go through your program come out with lower levels of anxiety? You would be extremely different. So whose house would you be in? You would be in the H1 or the HA, the H alternative's house. The hypothesis alternative says there is a difference, there's a change, there's an influence, there's a relationship, there's an association. In other words, you are different than the 95% norm. You are different than what everybody else is already doing. So you would actually be over here, or some people see it as HA. I'm going to use H1 moving forward, right? You would be here. And because there's two tails, what do we call this kind of hypothesis test that we're actually going to be running? Because there's two places that you could be extremely different. On the lower end, the negative side, or the positive end, then that means that you have a two-tailed test. So two-tailed test. A two-tailed test says there is a difference, but you're not actually saying where the difference is. You don't know if you're going to lower something or increase something. You don't know if you're going to be on the positive end or the negative end. You just know you are going to be distinctly different than everyone else. And you would hope that your program would yield a different result. In other words, you are in the tail, or what we call the H1's house. Anytime you're going to run a hypothesis test, you're going to test against the null hypothesis. The null hypothesis is the population. In other words, the null hypothesis is the mu. You are the H1, the M. You are going to be the sample. The sample is going to be run against the mu. And you're going to see, is my sample going to lead to a distinct difference than what the population is already doing? And that's why we talk about the idea of the standard error. And if you remember when we were talking about in class or from previous videos, you're going to learn that the standard error is simply the standard deviation. But the standard deviation is distinctly different than the standard error. And we'll talk about that in a few minutes, why they're distinctly different. But for now, let's first start talking about hypothesis testing and understanding where the HO is, the 95%, the no change, no difference area, and the H1, which is the tail, the places where there would be a difference. Then that brings us into step 2. Once we've actually stated, okay, this is this person's house, this is the other house, we're running a two-tailed test, or we can have a difference on the positive or negative end, lower or higher. We also have to decide, well, where does the tail begin? How extreme in the tail do we have to be distinctly different than the rest of the population? In a one sample z-test, you're going to run it at this particular alpha level. It's called the 95%, or the alpha level of 0.05, right? 0.05 in the alpha level is simply your level of significance. You're running a test at significance level of 95% accuracy, and you have a 5% chance, in this particular case, 2.5 on the positive, 2.5 on the negative. You have a 5% chance to be distinctly different or extreme. So you have a 95% chance to yield the same result as everybody else, hence your level of significance, the alpha level. Once you actually have the alpha level, you go on to find your p-value. For the one sample z-test, you have something called the unit normal table. The unit normal table will tell you if you choose an alpha level of 0.05, that means you have 95% in the body and 5% on the tail in a two-tailed test, two-tailed, split in half, That means you would have to find the z-score of 1.96. And in the back of the book, in the actual unit normal table, 1.96 gives you exactly 2.5% in each of the actual tails, leading to a 0.05 alpha level of a hypothesis two-tail test. So in other words, what is your p-value? Your p-value, your probability value, is the 1.96 of a z-score, which is giving you a 2.5% probability chance in the tail, positive or negative. And in reality, what did that do for you? It created this, our critical region. Our critical region is 2.5% on the positive, 2.5% on the negative. The critical region is the place where you would be critically different or significant. This is the place where you want to be if you're saying that your program yielded a different result than everybody else's, because everyone else is in the 95% area. They were doing this result and you want to have a different result. So you would want to be here in the tail. Degrees of freedom we won't talk about yet, like I said, because it's not part of the one sample z-test. When we're talking about the actual 3, compute and analyze, that means we're actually going to run the test, which means we're actually going to use a real example to actually run the test. In this example, if we were to run it, we would use the formula z equals the mean of the sample minus the mu of the population over standard error of m, which is the standard deviation of the sampling distribution of means. And then what would we do? We would have this be a formula, which is the standard deviation divided by the square root of n, which means standard error of m is actually a formula. We have a formula within a formula if we were going to run the one sample z-test.